All right, they give us an interesting and fun, yeah, I said it, challenge here to come up with as many isomers as you can for C6H12. What that means is we're going to give you 6 carbon atoms, 12 hydrogen atoms, make as many different things as you can with them, as many valid molecules as you can. And you can just start throwing stuff at the screen here, but if you want to keep this organized, the system that I am going to try to use here, and I think you've seen me do this once in a prior question, is I'm going to make things that have 6 carbons in the primary, and then I'm going to try to do things that have 5 carbons in the primary, and that'll leave me one that I can put in the branch, a branch somewhere. And then I'm going to go to 4 in the primary, which will mean I have 2 left for branches. 3 in the primary, leaving 3 for branches. 2 in the primary, that'll leave 1. I'm sorry, what am I doing? 4 in the primary means 4 for branches. And 1 in the primary, which will leave me 5 for branches. Some of these are not going to be possible. I'm pretty sure you can't do a methane and then put 5 things with the branches on it, but having a structure like this at least gives you something that you can try. Also, now that we've learned about cyclics, when we're doing our molecules, we can do straight line structures, and we can also try to do cyclic ones with ring shapes, and we'll see if we can get any of those to work. So, starting with the simplest thing, 6 carbons all in a line. 1, 2, 3, 4, 5, 6. I'm not going to draw the bonds. Yes, I am. I was going to leave the bonds out to keep this from getting cluttery, but it looks weird without them. Here's 6 carbons all in a line. This is hexane so far. And what would this do for hydrogen? We'd have CH3, CH2, 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 CH3. So this has 6 carbons. How many hydrogens, though? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We're over on hydrogen. So we cannot use hexane as one of our molecules. How could we trim a little hydrogen off of this, though? Remember hexenes? If we put a double bond in this, to form that double bond, this carbon has to jettison one of its hydrogens. It's only got 2 now. And this carbon also has to lose 1 hydrogen to free up a hand. So that takes 2 hydrogens off. Now we've got 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and it all works. So this molecule, which is 1 I was going to say it's 1 hexene because that was the old system and I still kind of like that. Hex 1-ene is what they want. Pretend you didn't see that. Hex 1-ene is a valid molecule. And we could move that double bond over to here, not in addition to, but instead of what we had in the first one. And this would still be C6H12. I didn't update the numbers, but the double bond could be any place in this molecule and that would still work. So we would get hex 2-ene. We could put it here and get hex 3-ene. Could we put it there? No, because that instead, if we numbered from the other end, that would just be hex 2-ene again. So it would go 1-ene, 2, 3, 2, and 1 again, depending on the location. These 3 here are valid isomers for C6H12. While we're at it, what if we make a ring with 6 carbons all in the primary? 1, 2, 3, 4, 5, 6. We'll single bond everything and see how that works out for us. What does that give us for hydrogens? We get H2, H2. They're all going to be 2s, aren't they? And 2 times 6 is 12, so this, which is cyclohexane, is also a way to get C6H12. In this case, you get rid of two hydrogens, not because you've got a double bond, but because when you bend this around and make it a ring, the two carbons on the end that have to grab onto each other each release a hydrogen, and that brings us down from C6H14 to C6H12. So, we have successfully found 4 isomers so far. And you're thinking, that took him a few minutes. This is going to be a long video. I'm afraid you're right. I'll try not to make it super drag, but to get all of these, to get all of the molecules that we're supposed to find here is actually a bit of a slog. Sorry about that. I also have written these in an unsmart place, so I'm going to have to relocate some stuff to keep the screen kind of readable. Okay, I reorganized the screen real fast so we'd have a little more room to do stuff. So here's our scoreboard so far. We've got 4 isomers, and the next thing I was planning to try was 5 carbons in the primary, which would leave 1 for a branch. So if we go 1, 2, 3, 4, 5 in the primary, and then we can't put a branch here, right? Because then it wouldn't really be a branch. We just have a 6 carbon primary. So the first place we could put a branch would be there. Oops, not that. And what does this do for us hydrogen-wise? We'd get 3, just 1 because 3 bonds, 3, 2 because we're in the middle, 2 because we're in the middle, and 3 because we're on the end. 3, 6, 7, 8, 9, 10, 11, 12, 13, 14. Again, we're over on hydrogen. So we need to lose 2 hydrogens someplace. And again, only way to fix that is to throw in a double bond someplace. So if we put a double bond here, now our primary is what? Pent 1-ene. And we have a methyl group on it. Put it in this existing group. So we have pent 1-ene, and it's got a methyl group on carbon number 2. So 2-methyl pent 1-ene. What could we change about that? We could move the branch over and get 3-methyl pent 1-ene. We could move it over further, 4-methyl. And could it be on the very end? It couldn't be on the very end because then it wouldn't be a pentene, it would be a hexene. But it could be all the way over to carbon number 4, and that would still be all right. Also, we could take that double bond and move it over 1 spot, and then we could move our branch again. So let me just show what that means. Instead of having a double there, we could say that our double is now in that position. So now instead of pent 1-ene, we have pent 2-ene, and we still have the ability to take this methyl group and scoot it around from one spot to the next. So if we did that, we could have 2-methyl pent 2-ene. We could have 3-methyl pent 2-ene, 4-methyl pent 2-ene. And we could also put the double, could it be? No, if we put the double here, I was thinking we could do pent 3-ene, but that, if you number it from the right-hand side, would still be pent 2-ene. So that's actually all the flex that we have. We can make pent 1-ene, pent 2-ene. There is no pent 3-ene because if you just switch the numbering and it turns into pent 2-ene. So these are the only isomers that we can get with 5 in the primary and 1 in a branch. At least if the molecule is linear. One more thing we can look at here. What if we try this 5 primary 1 branch with a cyclic? Can we even make that work? What does a 5 primary cyclic look like? We're going to have 5 carbons in a pentagon. Single bond, all that. And then throw another carbon off the end. Can we do that at all? We're going to have H2, lots of H2s here. This has 3 bonds, so only room for 1 hydrogen, and then we get 3 on the end. What does that do for us hydrogen-wise? We have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that actually works. We could have methylcyclopentane. There doesn't seem to be any problem with that. That checks all the boxes. Unfortunately, there's no variety to this. There's no double bonds we can move around. There's no other places we can put this methyl group. No matter where we put it, that would be carbon number 1, so there's no numbering to change. So we only get 1 isomer here, and it's methylcyclopentane. Still, we've done 6 and 0 and 5 and 1, and we're coming up with a good batch of different isomers. I'm going to stop this recording here, and I'll pick up another one some other time where I continue to do more isomers. But hopefully you can already see the pattern, and if you try to do 4 with 2, 3 with 3, 2 with 4, and 5 with 1, it'll give you some kind of structure for figuring out as many combinations as you can. This isn't for points, really, so don't burn the rest of your life working on this, but hopefully it'll give you some practice at different ways that you can combine these and coming up with the names for them, which is always good practice. So have fun, quote unquote, and we'll see you in the next one.